myself Prayak Patel, working as assistant professor in IT ICT department of LJ Institute of Engineering and Technology. Now in today's video lecture, I will discuss about the new concept of the graph theory is a homeomorphic graph. Now first we understand what is the homeomorphic graph and how we can check given two graph is a homeomorphic or not. So first understand the definition of the homeomorphic graph. The loop-free undirected graph G1 equal to V1 E1 and G2 equal to V2 E2 are called the homeomorphic if they are isomorphic. So we can say that first condition for the homeomorphic is if the given two graph G1 and G2 is isomorphic, then we can simply say that this graph is a homeomorphic. Now second condition for the homeomorphic is if they can both be obtained from the same loop-free undirected graph H by a sequence of elementary subdivision. Now we already know what is the elementary subdivision in our previous video lecture. So elementary subdivision means remove the one edge from the graph and add new edges in the graph. So simply we can say that between the two nodes we can add the one another node and this another node is considered as a new node. So this makes the graph as a elementary subdivision. So by adding the elementary subdivision we will get the both the graph is considered as a undirected graph obtained from the graph H. So we can say that these two graph as a homeomorphic graph. So in this graph, this given graph is a graph H. Now for this graph find the another graph as a subdivision graph. So in this graph subdivision graph first as a add the one node B between the A and B. So simply we can say that the remove edge A to B and add edge A to B and B to B. So we can say that this graph is a homeomorphic graph. Now this homeomorphic graph will obtain by subdivision operation. So we perform the operation subdivision operation between A and B here. Now another subdivision operation is like add the one node between the A and D as a Y, add the another node as a Z between B and E, add the another node W as a between C and E. So consider the last figure is also considered as a subdivision graph from the H. Now we consider the obtained two graph as a subdivision graph. So subdivision two graph is considered as a homeomorphic graph if they both are considered as a subdivision graph. So here we can say that graph number 2 and graph number 3 as a homeomorphic graph. Now for the homeomorphic graph, for example, first graph G is a one graph and another graph H is a considered as a another graph. Now for this graph G and H both are obtained from the same graph after applying the subdivision operation. So here we can say that if we perform the subdivision operation on G once again, then we will get the resultant graph as a G dash. Now we also apply the subdivision operation on H, then we get the another graph as a H dash. Now here we can say that G and H, here G and H is a homeomorphic graph. Now for G dash and H dash, we can say that G dash and H dash are the isomorphic graph because both graph are similar graph. So we can say that after applying the subdivision elementary operations, we will get the isomorphic graph also. So here G and G dash are the homeomorphic graph, H and H dash are the homeomorphic graph, but G dash and H dash are the isomorphic graph. Now for the isomorphic graph, we can say that G graph is a given graph. Now we obtain the graph G1 from G after applying the sub elementary operation between A and B. So here we consider the remove the edge A to B and add edge A to W and W to B for elementary subdivision operation. Now for the second graph G2, we remove the edge between A and E and add the edge A to Y and Y to E. So simply we can say that they add new node as a Y and degree for the Y node equal to 2. Now same way in graph G2 X is also added. So graph G2 is also considered as a obtained from the graph G. So we can say that graph G1 and G2 both are the homeomorphic graph. because both are obtained from the graph G after applying the sub-elementary division operation. So also consider the graph G3. In graph G3, we also perform the different elementary subdivision operation between A and B, A and E, B and D, and C and D. So we can say that G3 is also homeomorphic with G1 and G2. So this is a simple concept of the homeomorphic graph. If two graphs are homeomorphic, they are either both planar or both are non-planar. So this is a main concept of the homeomorphic graph. If both graphs are homeomorphic, then both are planar graph or both are non-planar graph. For example, H is a given graph. Now find the, after applying the subdivision operation, we will get the graph next as a second figure. Now here we add the Y, Z and W, three ACs. So we can add another graph or add the another elementary subdivision between A and B. Then resultant graph as a graph 3. So remove the edge A to B and add the edge A to V and V to B. So this two graph is considered as a same graph, or means we can say that the both graph are homeomorphic graph. Now for the homeomorphic graph, if both graph are homeomorphic, then both are planar or both are not planar. So here both the graph are planar. So this definition is also satisfied for the planar graph. Now for the planar graph, we consider the one theorem as a Kurto's theorem. So here in this theorem, a graph is non-planar if and only if it contains a subgraph that is homeomorphic to either K5 or K33. So here we can say that the K5 and K3 graph is already Now how we can check this theorem? So for example, here we consider the Peterson's graph as a graph, given graph in figure A as a Peterson's graph. Now for this Peterson's graph, we draw the graph as a K33 form or in the form of K5. Now for this graph, we consider the subgraph of this Peterson graph as a figure B. Now in this subgraph, we remove the some edges because this graph considered as a subgraph. So we remove the some edges or some node and we will get the resultant node as a graph B. Now for this graph, how we can check this graph is a planar or not? So in figure A, we have a graph as a Peterson's graph, and in figure B, we use this subgraph or find the subgraph for the Peterson's graph, and this Peterson's graph subgraph is a homeomorphic to K33. Then we can say that this is a non-planar because K33 is a non-planar. So this subdivided graph or subgraph of Peterson graph is a homeomorphic to K33 because after adding the two nodes, or we can say the removing the any edge and add the two edges, or we can reverse operation is also possible for that. So we can say that this graph is a non-planar graph because K33 we already know that K33 is a non-planar. So this given graph is also considered as a non-planar because this is a homeomorphic to each other. Now how we can check this? Because for K33 different possibilities how we can draw the different edges. So these all are the different way for representing the edges. So these all the combinations are given here. Now first graph is your graph as a K33 graph. Now for obtaining this first graph, we have to perform some operation on previous graph. So for example, here one node available between D and B and node is C. Now another node available between B and J is G, so represented in third figure. Now another node added, here we can say that the H between F and J. Now another node added I between D and F. So this graph number 5 is our previous graph, and from the previous graph we find the K33 graph, or from the K33 we will get the figure number 5 after performing the sum operation. So we can say that this is considered as a homeomorphic graph. So we can find the homeomorphic graph with K33, then we can say that this graph K33 is not planar, then this given graph is also as a non-planar. Now see this operation here, how this operation can be performed. So remove the one node from this graph. So we will get the resultant graph is like this. Then combine the two node and we will consider only one node. So remove the two node and add one node. Now resultant graph is considered as a K33 graph. So we can find the K33 graph from the Peterson's graph. So this is a process how we can find the Peterson's graph to K33 graph. And for the K33 graph, we already know K33 is not planar. So this graph is also considered as a non-planar graph. Now next concept is region in planar graph. Now what is the region and how we can find the region for the graph? Now consider the planar graph G equal to VE. A region is defined to be an area of the plane that is bounded by edges and cannot be further subdivided. A planar graph divides the plane into one or more regions. One of these regions will be infinite. So here we can say that between the two nodes we consider the graph divided into the number of regions. For example, we have two types of region. First one is a finite region and second one is a infinite region. Now finite region means if the area of the region is finite, then the region is called the finite region. For example, in this graph divided into some regions, but each and every region is considered as a region between the nodes. So area covers by the multiple nodes is a region. So here for example R1 region, R2 region, R3 region, this three region is considered as a finite region. Close boundary between this graph or nodes is considered as a finite region. Now R4 means R4 considered as a outer part of each and every edge which have considered as a outer edge. So R4 region is considered as a not a finite region, so it is called the infinite region. If the area of the region is infinite, that region is called the infinite region. A planar graph has only one infinite region. For example, R4 considered as a infinite region. Now in second figure also we find the region. So here different sub portion of the graph is considered as a region. So here R1, R2, R3, R4, R5, these five are the considered as a finite region. Now infinite region means outer side plan considered as a R6 as a infinite region. So this is a simple concept of the region. Now what is the degree of region? Now we already know what is the region. Now how we can find the degree of the region? For each region R in a planar graph, we can say that the not consider as a graph as a multigraph. So here we can say that for any region R in a planar embedding of a graph or multigraph, the degree of R denotes the degree arc. Is the number of edges traversed in a close walk about the boundary of R. So here number of edges covered in this region is considered as a degree of R. For example, region R1 connected with three edges. So here we can say that degree of the R1 equal to 3. Now for the region R3, degree equal to 3. Now for the region R2, what is the degree? So here consider the degree for R2 like consider all the connected edges. So here we can say that the edge is connected as a total 7 because here one edge is available here. So this edge is considered 2 times because here both the side we visit the edges. So move into the each and every edges and find the degree of the region. So for example R4 degree is also as a 7 because we consider this last edge 2 times. Now for the same way how we can find the region? So in this second figure, what is the degree of R1? So degree of R1 equal to 5 because 5 edges connected in region R1. Degree of R2 equal to 3 because 3 edges connected. Now next is a degree of R3. Now degree of R3 equal to also 3. Degree of R4 equal to 7. Now why we consider degree of R4 equal to 7? Because when we move or walk, close walk like A to B, B to G, G to H, H to G. So here H to G is once again we visit at upper side one time and at lower side one time. Then G to F, then F to D, then D to A. So here we can consider the total 7 degree for the region R4. Now total degree of the region we find using the addition operation. So here operation is like sigma I equal to 1 to n degree of Ri. So it is the total degree. Now for the second graph, total degree of this graph is considered as a 18. Addition of 5 plus 3 plus 3 plus 7 equal to 18. Now 18 means we can say that 2 into E, because here number of node multiplied by 2 equal to total degree of region. So we can say that 18 equal to 2 into 9. So 9 edges available in this second graph. So this is a degree of region. Now in degree of region, another example for the degree of region for the loop or for the multigraph also. So for the loop, for example, R2 in first figure consider as a loop. So R2 degree equal to 1 because his region R2 is considered only one edge. Now for the multigraph also we can find the region. So here in first graph R1 consider as a degree 6, R2 degree equal to 1, R3 degree equal to 5 and total degree equal to 12. So 2 into 6 equal to 2e. Now for the second graph, here we can say that R1 and R2 having a multiple edges. So we can say that R1 degree equal to 2, R2 degree equal to 2, R3 degree equal to 4, R4 degree equal to 2 and R5 degree equal to 5. Here one self loop as a R6 degree equal to 1. So total degree equal to 16. So satisfy the condition 2 into E. Now some theorem is also available for the degree or region concept. So here one theorem is considered as a Euler's formula or Euler's theorem. Now in this formula, what is the concept? Let G equal to VE be a connected planar graph or multigraph with V equal to mod V equal to V and mod E equal to E. That means length of the node equal to V and length of the edges equal to E. Let R be the number of regions in the planar graph. So here we can say that V as a number of nodes, E as a number of edges and R as a number of regions in a graph. Now one of these region has infinite area and is called the infinite region. So formula is V minus E plus R equal to 2. So this is a formula considered as a Euler's formula. Now proof of this formula is, the proof is by inductions 1. So here if E equal to 0 or 1, then what is the process? Then G is isomorphic to one of the graph in this figure. So here this type of graph can be possible for the node 1 or node 2. First graph A is for the node 1. Now in the for node 1 we can say that what is the V? V equal to 1. What is the E? E equal to 0 because no any is. Then what is the R? R equal to also 1 because only one region. So we can say that V minus E plus R equal to 1 minus 0 plus 1 equal to 2. So they satisfy the condition V minus E plus R equal to always 2. Now in second figure B, we consider the V equal to only one node B. Now E equal to only one edge. So V equal to 1, E equal to 1. Then what is the R? R considered as a 2 region because inner part is a 1 region and outer part is a another region. So region equal to 2. So we check the condition V minus E plus R equal to 1 minus 1 plus 2 equal to 2. Now after that third figure. In third figure we have a two node C and D. So we can say that V equal to 2, one edge is available. So E equal to 1, R equal to consider as a only one region. So V minus E plus R equal to 2 minus 1 plus 1 equal to 2. So this also satisfy the formula for the Euler's. Now in this graph also satisfy the formula because V equal to 5, E equal to 7 and R equal to 4. So satisfy the total equal to 2. Now another theorem for this concept is, let G equal to VE be a loop-free connected planar graph with V equal to mod V equal to V and mod E equal to E, E greater than 2 and R considered as a region. Then 3R less or equal to 2E and E less or equal to 3V minus 6. So how we can check this? So proof of this theorem is, since G is a loop-free and is not a multigraph, the boundary of each region contain at least 3 edges. Hence each region has the degree is always greater or equal to 3 because they satisfy this condition. Now consequently 2e equal to 2 mod e equal to the sum of degrees of the region. The region determined by G and 2e greater or equal to 3e. So from Euler's theorem we can say that V minus E plus R equal to 2. So here we write 2 equal to V minus E plus R. Now in place of R we represent the R equal to 2 by 3e. So resultant state as a V minus E plus 2 by 3e equal to we subtract the minus e with the 2 by 3e. So result is a v minus 1 by 3e. Then simplify the statement. So resultant statement is a 6 less or equal to 3v minus e or e less or equal to 3v minus 6. So this is a theorem. Now for this theorem we understand using example. So for example in this given graph, what is the v? V equal to 7. E equal to 9. 9 edges are available and R equal to 4 because 4 region are available. Now here we can say that 3R less or equal to 2 is satisfied or not. Now here 3 into R, so we can say that 3 into 4 because 4 region less or equal to 2 into 9. Now satisfy the condition here because 12 less or equal to 18 is satisfied. So this theorem is true. Now next check the second condition as a E less or equal to 3V minus 6. So E equal to 9. V equal to 7. So 3 into 7 minus 6. So we get the result as a 15. So 9 less or equal to 15 is satisfied. So second condition is also satisfied for this example. Now for these two example also we have to find this consider as a satisfying condition or not. Now here prove that complete graph K4 is a planar or not. Now we know K4 graph figure is like this. Now this figure also represented in another way like second figure. So K4 is a planar graph. Now prove using this formula. Now here in K4 we have a 4 vertices and 6 edges. So V equal to 4, E equal to 6 and region R equal to 4. Now 3R less or equal to 2E is satisfied or not? Check here. So 3 into 4 less or equal to 2 into 6. So 12 less or equal to 12 condition is satisfied. So we can say that this is a planar graph. Now E less or equal to 3V minus 6. So E equal to 6, 3 into 4 minus 6. So we can say that 6 less or equal to 6. This condition is also satisfied. Means we can say that K4 is a planar graph. Now prove that complete graph K5 is non-planar. Because we already know K5 is not planar. But we use the formula and find how this graph is considered as a non-planar graph. Now for this graph, what is the value of V and what is the value of E? So here we can say that graph having a 5 node. So V equal to 5, 10 edges. So E equal to 10. Now use the formula E less or equal to 3V minus 6. So in this case 10 less or equal to 3 multiply 5 minus 6 means 10 less or equal to, we will get the result as a satisfying condition is not possible because 10 less or equal to 9 is not possible. Means this graph is not considered as a planar graph according to this theorem. E less or equal to 3v minus 6 is not satisfied. So this is a simple case how we can find this graph is a planar graph or not using this example. Now next we understand in this lecture as a how we can check given graph is a planar or not using this some theorem also. So thank you for watching this video.